Okay, our study for today is the next in our mini series here on the effects of shoe properties on running economy. This is a 2012 study by Franz et al. Titled Metabolic Cost of Running Barefoot versus Shod is Lighter Better. This is one of my favorite studies on this topic of shoe properties and running economy. It's a nice follow up to the Frederick study we read last time, and that attempts to isolate the two main shoe properties that we introduced in the Frederick study that affect, or at least are investigated in terms of their effects on running economy: the mass of the shoe and the cushioning of the shoe. The Frederick study was comparing two shoes that differed in their cushioning properties. One had the Nike Air Pocket, one didn't. And those shoes also differed on their mass, but that wasn't a factor that they manipulated, or wasn't a factor that they were controlling for. It was sort of controlled for in the sense that the more cushioned shoe was also the heavier shoe, and that was the shoe that had the lower rate of oxygen consumption for running. And so, since it was the heavier shoe, we're not able to say, well, it just had lower oxygen cost because it was a lighter weight shoe. Well, it was actually a heavier shoe, so we are presumably then attributing the improvement in oxygen cost to something other than being a lighter shoe, because it wasn't a lighter shoe. But they weren't really experimentally manipulating the effect of mass there in isolation of cushioning. That was exactly what they attempted to do in this study. They manipulated the mass of the shoe systematically as like a continuously adjusted variable. And through that, we're able to experimentally isolate the effect of shoe cushioning as a categorical variable. So, running in shoes with some cushioning in the shoe versus running barefoot with no shoe cushioning at all, but while experimentally controlling for the confounding effect of mass, and that when you remove shoes and run barefoot, you're not just changing the cushioning of the foot ground interface, you're also changing the mass of the shoe foot complex by taking that mass of the shoe away from the foot. So they came up with what I think is a really clever and creative experimental design for isolating these things. Motivation for the study: there's two main motivations for this study. One is highlighted here early on in the abstract, where they say, and this is motivated by some earlier research by Frederick also, where that every 100-gram change in shoe mass affects the rate of oxygen consumption, so running economy essentially, by about 1%. Okay? And are these meaningful numbers here? Is 1% a meaningful change in running economy, and is 100 grams a meaningful change in shoe mass? Or is this such a big change in shoe mass that shoes don't even vary by that much, so this is a pretty trivial effect? 1% here is indeed a substantial change in the energy cost of running and in running economy. The Nike Alpha Fly shoes that we've talked about a couple times, the technologically advanced shoes that Eliud Kipchoge and other marathon runners are using these days to run very fast times and set world records in marathon in under 2 hours and these things. Those type of shoes that a lot of companies are making now, not just Nike, but shoes with kind of advanced materials in the midsole and carbon fiber plates and very light masses of the shoes and these things. They can improve the running economy compared to a standard running shoe by ballpark like 3 to 5%. Sometimes a little bit less, sometimes a little bit more, but on average, 3, 4, maybe 5% if you're real lucky. And that's a substantial change in running economy. Any competitive marathon runner, if you tell them I can instantly improve your economy by 3 to 5%, they're going to love that. That's a major advantage in terms of performance and in potential for fast racing times in a race like that. So 1% here, and certainly 2%, 3%, if it's a big change in mass, is indeed a meaningful change in running economy. What about this 100 grams here, right? Ideally, if we want to get a big potential to affect running economy, we would want this 100 grams to be a pretty small fraction of what a shoe could feasibly weigh. And this is indeed a pretty, not a tiny fraction, but a reasonable fraction of the range of running shoe masses for normal running shoes. A really, really light running shoe, like the lightest possible racing flat that you would run, a fairly short race in, might be ballpark like 100 grams or so. And then on the other extreme would be like your heavy bulky, like really cushioned, really just a lot of construction to it shoe for like daily training or like a trail running shoe or something like that. And those could be up to 500, maybe 600 grams per shoe or so. So 100 grams here is indeed a meaningfully small enough fraction of running shoe mass. This is well under the range of normal masses for running shoes. So both of these are meaningful numbers. The other motivation for this study, and this hasn't uniformly been found in like every study that's ever done this comparison, but the majority of studies that have compared running economy in running shoes versus running barefoot have found that you're more economical when you run barefoot. Now, the assumption there is typically that, well, when I remove my running shoes, I'm removing mass from the feet. And so that, as long as the shoes have some substantial mass to them, like 100 plus grams, which is pretty normal, that there alone should improve my rate of oxygen consumption by 1%, 2%, 3, 4, maybe 5%, depending on how heavy my shoes are there. But the kind of confounder there is that when I remove the shoes, I'm not just removing the mass of the shoe, I'm also removing the cushioning of the shoe. So it's difficult to tease out how much of any change you might observe in running economy is due to a change in mass versus due to a change in some other property that the shoe endows your foot with, like the cushioning of the shoe. And so that's what they were attempting to isolate here, the influence of shoe cushioning on the energy cost of running and running economy in isolation of the confounding effect of mass. The experimental design here was pretty similar to the Frederick experiment. They had 14 healthy male runners. They excluded 2 of them for various reasons and ended up just having 12 subjects in the study. And they ran on a treadmill with hooked up to a computer and a pulmonary gas exchange measuring system to measure their oxygen consumption and their energy cost of running. And they ran on the treadmill in conditions wearing a running shoe and in conditions running while barefoot without wearing any shoe. Okay? The shoe that they wore is mentioned down here as a Nike Mayfly. That wasn't a shoe that I'm familiar with, so I Googled it, and here's a picture of it here. It's a very lightweight, looks like kind of a woven shoe that, I don't know if Nike still makes this shoe, but it was available in 2012, evidently. And it's pretty lightweight running shoe. They mentioned the mass later on here, further down in the study, right here. And of course, the mass of the shoe will depend on the size of the shoe, whether it's men's or women's and the size. But ballpark, this shoe weighed about 140 grams per shoe, which is a pretty light running shoe. That's on the lower end of like masses for shoes that you would use for normal running. Okay, what they did here that was really clever and kind of the new piece for the study here was that, remember the confounder that I mentioned here, if you're going to compare barefoot running to shod running, is that it's difficult to isolate the effect of the shoe cushioning versus running barefoot with no shoe cushioning, because you're changing 2 things at once there when you take off the shoes. You're removing the cushioning and you're removing the mass of the shoe. And mass of the shoe has a big effect on energy cost of running. So we can't isolate the effect of cushioning by just taking the shoes off. What they did here to control for that mass effect was the participants didn't just wear the shoe or didn't just run barefoot. They wore this little wrap around the upper of the shoe or around the heel / dorsal part of the foot here. And this little wrap that they wore had little pockets in it that you could insert little metal weights into. So what they did here to control for mass was they would take off the shoe, and that shoe weighed about 140 grams. And then in the wrap here, they would add weights to it to add back that 140 grams, such that you could run barefoot, but with the mass of the shoe that was taken off added back to the foot here. So then we can have a comparison where mass is the same, and the only thing that's different is whether I'm wearing the shoe or not, and whether I have that cushioned interface, the cushioned midsole on the bottom of my foot, versus nothing on the bottom of my foot, just running barefoot. Key punchline here, key result is in figure 4. In each of these figures here, both the top one and the bottom one, on the x-axis is showing the multiples of shoe mass that were added to the bare foot. In the black dots, the first multiple of shoe mass, so the change here from 0 to 1, was added by the mass of the shoe itself. Okay? In the white dots, that first multiple there, so going from 0 to 1, is going from a purely barefoot condition with nothing on the foot up to a condition where one multiple of the shoe mass was added to that wrap around the bare foot. Okay? So top to bottom here, this allows us to make a comparison between running in the shoe versus running without the shoe, but with the mass of the shoe that was removed added back to the foot. So no confounding effect there in terms of these top to bottom comparisons of a difference in mass. The mass of the whole foot shoe wrap complex was the same in all of these comparisons that have the same value on the x-axis there, whether it's 1 or 2 or 3. So in these black dots, they were wearing the shoe. In these white dots, they were barefoot, but had the mass of the shoe added back with little weights on that wrap. These other values here on the x-axis, where it's multiples of shoe mass 2 and 3, that's where they were wearing the shoe and the wrap with an additional mass of the shoe added to the wrap. Or up here, they added 2 masses of the shoe, and up here 3 masses of the shoe. And this was just to see if the results that they found kind of generalized to lots of shoe masses or just to this specific relatively light shoe mass. So just kind of increasing the versatility and generalizability of the findings there by investigating lots of hypothetical shoe mass conditions, not just one shoe mass condition. On the y-axis here in the top graph, and again, the white dots are running barefoot in all cases, and the black dots are running in the shoe in all cases. On the top graph, the y-axis is the rate of oxygen consumption, that key variable in our running economy metrics. And on the bottom is that same data, but expressed as the percent change in oxygen consumption relative to the far left white dot here, which was running barefoot with no mass added to the foot. Okay? And so that's why on the very far left here, where the x-axis says 0, you don't see a black dot, because that would have been impossible to measure. You would have to run in a massless shoe to be able to have a black dot there, which violates every law of physics I know of. You can't have a shoe that has literally 0 mass. Okay, regardless of whether you were running barefoot in the white dots or running shod in the black dots, the dependency of the running economy on shoe mass followed the kind of Frederick thumb rule there in both of those cases. It was a little bit larger in terms of the percent change in VO2 per 100 grams when you were wearing shoes, but I don't think the slopes of this top line versus this bottom line are significantly or meaningfully different there. So ballpark 1% change in rate of oxygen consumption per 100 grams of mass here change in the foot shoe mass of the foot shoe complex. So just backing up the relationship there observed in previous studies on shoe/foot mass and change in the energy cost of running. So if you want to run more economical, a lighter shoe or lighter foot shoe complex does indeed appear to be beneficial based on the data in this study and on other studies that have examined that. The new, more interesting piece here is, remember, we have these comparisons from top to bottom where mass is controlled for here. So the only thing that's different, for example, between this black dot on the bottom and this white dot on the top is the cushioning between the foot-ground interface. In the top, I'm barefoot, and on the bottom, I'm wearing a running shoe with some substantial cushioning between the feet and between the ground. The mass of the foot-ground or foot shoe wrap complex is the same between these two comparisons here. And notice here, it's easier to see if I look down here at percentages, notice here that every time I compare running barefoot versus running shod, when mass is controlled for, when the mass lost by removing the shoes is added back to the mass of the foot, so that the only thing that's different is the cushioning between the foot-ground interface, it's more economical for me to run in the shoes. And how much more economical? Well, roughly an improvement or roughly a decrease of about 3% in my VO2. So that's a pretty substantial change in the energy cost of running. If you go and tell a competitive runner, hey, I can improve your VO2 and your running economy by 3% instantly, that's an impressive advantage in performance. Everybody's going to want that. Other interesting piece here in the findings is that if you go clear to the left here and draw a straight line out to the right, what that's showing is the results relative to the VO2, or the rate of oxygen consumption, when running barefoot. So anytime you see a dot above this line, the running economy was worse than running barefoot with no mass added to the shoe. And anytime you see a dot below that line, the running economy was better than the economy of running barefoot with no mass added to the shoe. So you can see here some additional support for a benefit of shoe cushioning on the economy of running. Even if I take the case where I just compare running in my lightweight shoes versus running in no shoes without controlling for mass, I was still about 2% more economical when I was running in those shoes. Even if I go ahead and double the mass of the shoes, which is this dot here, I was still on average about 1% more economical than when I ran barefoot. It wasn't until I tripled the mass of the shoes that I was actually a little bit less economical, about 1% less economical than when I was running barefoot. So this isn't to say that all the previous studies on running barefoot being more economical than running shod are bogus or have some technical flaw, but one thing that most of those studies were doing was comparing pretty heavy running shoes, like shoes that are in excess of 3, 4, maybe 500 grams here, to running barefoot with no shoe mass added to the foot. And so this is suggesting that that effect of barefoot running kind of categorically decreasing the energy cost of running versus shod running may not be a categorical effect. It may only extend to running in fairly heavy shoes to begin with. Here we see if we were running in a very light shoe, I was actually more economical than running literally barefoot with nothing on my feet. And even if I increased the mass of that shoe by 100%, I was still more economical than running barefoot. So the finding that barefoot running is more economical than shod running may be only applicable to fairly heavy running shoes. You may be better off economically by wearing a pretty light running shoe with some cushioning in it. Last bit that I wanted to highlight here was a portion of the discussion that they get into here, where they're trying to explain why the cushioning here appears to have a beneficial effect on a running economy. And I got into that a little bit with the Frederick study last time in terms of mechanisms, not just observing that the cushioning affects the energy cost, but trying to explain why the cushioning affects the energy cost. One suggestion that they make here was that they highlighted that running in the shoes versus running barefoot changed the biomechanics of the individuals who were running. For example, they note here that when the participants ran in shoes, their stride length was about 3% longer than when they ran barefoot. And that's pretty typical. Many other studies have shown a similar result to that when you take somebody's shoes off, they tend to shorten their stride up a little bit and increase their stride frequency a little bit to run at the same speed. So that, and as we saw a couple lectures ago in the Morgan study, changes in stride length and stride frequency can meaningfully affect the economy of running, especially if they're large changes. Is 3% here a large change in stride length? I would say in most cases, probably not. That's probably on the threshold of like what's large enough to measure consistently and large enough to actually have a meaningful measurable cost on the energy cost of running. In most cases, I would argue that this is probably not a big enough effect to explain substantial changes in running economy. This is probably too small, I would say, to explain differences on this order of magnitude here, 3% improvements in running economy. So it could be a factor, but not one that I think is probably a big enough confounder here to say, well, they should have repeated the study while controlling for stride length and run a metronome to have everybody run at the same stride length in shoes or without shoes. That would have isolated this effect, but I don't think it's accounting for the lion's share of the results here in terms of improving running economy with some cushioning under the foot. The other explanation that they forward here that I think is the more likely explanation is this cost of cushioning hypothesis. And this is the idea that there's an optimal amount of cushioning, an optimal set of mechanical properties of the interface between the feet and between the ground, whether it's the cushioning in the shoe itself or the mechanical properties of the surface that you're running on, like concrete versus grass versus sand. There's some combination of mechanical properties of that interface that is optimal for the energy cost of running, and that if you design a shoe that has the ideal properties, the right amount of stiffness and the right amount of damping, that you could, in theory, have a set of mechanical properties there that are ideal for kind of bottoming out the rate of oxygen consumption in running and having the best running economy. Those two terms that I mentioned there, stiffness would be how much the interface deforms, or the midsole in the case of a shoe deforms for applying a certain force to it. And damping gets a little complicated, but damping kind of manifests itself as how much energy is lost with each step. The more damped something is, the more energy it's going to suck out of your stride, or the more mechanical energy it's going to suck out of your stride with each step you take. So you can certainly envision some combination of those kind of two key surface condition interface or surface condition parameters that would certainly affect the energy cost of running and maybe be tuned to optimize the energy cost of running. The idea that they suggest here is that by lacking the cushioning between the shoe, the cushioning of the shoe, that you are deviating from the optimal foot-ground interface there in terms of running economy, and that you're having to accomplish the necessary actions of the movement using muscular effort, using the muscles of the leg, rather than having the foot ground or the shoe interface provide some of that action and some of the energetics there, and that extra muscle activity that you have to do when you run without that cushioning incurs what they call a metabolic penalty. No data here necessarily to suggest that or to test that hypothesis, but it is, I think, a compelling explanation for these results, that the cushioning allows for a reduction in leg muscle activity, or reduction in how much effort the muscles have to use to move you across the ground at a certain speed. And we'll examine one more study here before we move on from this topic that also supports that idea that some certain amount of cushioning in the shoe is beneficial, and mechanically why certain types of cushioning in the shoe and certain amounts of stiffness, certain amounts of damping can be beneficial for the energy cost of running. Okay, that is it for today, and that is it for this week, and we will see you next time.